day week,
Yes.
and then and then we have a 4-day week after this week too. That's right.
I'm excited now.
Invest in a calendar, but
I wasn't keeping track of it.
yeah, that's okay. All right. So today I will start by taking questions. If you have homework questions or other questions, just kind of generally, anything is fair game. Chanel, we'll start with you.
Can you do number 15?
Number 15 from the problems. Copy and drop. So it says use a function grapher to. Can we stop talking while I'm talking, guys? Thank you. To find and classify all local minimums and maximums, round your answer to the 100. And I think this one is just like, you looked at it and like, wait a minute, I didn't see that other one. Is that what you saw on this one, Chanel, or no?
What do you mean? I saw the other one.
Let me look at it real quick. I can't remember if we fixed this or not. There was one of these where it was like really ambiguous as to what was going on. Let me look at what this is. Nope. That should be good. Okay. So I see one local maximum here, and I see one local minimum here.
Yeah.
To find these, the coordinates for these, I'm going to press second, and then trace. And then to find the maximum, which I'm going to do first, I'm going to use the maximum command. Press enter. The calculator now is going to ask me a series of questions. So the left bound wants, the calculator is asking me to move my cursor so that it's on the left side of that maximum. So that's fine. Anywhere to the left of it is okay. And then press enter. Now it says, now I need a right bound. So I'm going to move that cursor somewhere to the left of it. So that looks good there. I'll press enter. Then asks for a guess. As long as there's only one maximum in between the left bound and right bound I gave, the guess doesn't matter. So I'm just going to press enter here. So there's my maximum from my calculator. So I would just copy in these numbers rounded to the hundreds, so 2 decimal places. And then to find the minimum, I would do the same thing, except I'd use the minimum command.
Okay, yeah, I got it. I got the maximum minimums, right? I just didn't know how to use that function.
Oh, okay.
So
There you go. Fairly straightforward, right?
yeah.
Cool. No problem. Ariana.
Can you do 12, please?
Sure. So 12 asks us to find the range for the given function. So here, notice that it doesn't tell me specifically like how to do it. So would there be anything wrong with graphing this on my calculator and looking at the picture? No, right? The directions don't say you have to do this algebraically. They just ask you to find the range. So I could do this and say, oh, okay, looks like, let's see, that looks like the point 3, 2 there. So it looks like, I would say bracket 2 to positive infinity. That would be sufficient. If you wanted to do this algebraically, I will do that also for you, because I have a feeling that was kind of the question you were asking, more so than just like, yeah, and it's okay. So we know that the domain was 3 to positive infinity. Were you good with how we came up with that? Okay. And if I looked at the graph of this, I noticed that my function is increasing always, right? So my range is going to be h of 3, comma h of positive infinity. So I keep the same order. And then I keep the same inclusion for the bounds of my intervals. So the one with the positive infinity plugged in gets a parenthesis. The one with the 3 plugged in still gets the bracket. And when I plug 3 in for x, 3 minus 3 is 0. The square root of 0 is 0. 0 plus 2 is 2. Oops. And if I plug the infinity in, 3 minus infinity is still infinity. Square root of infinity is still infinity. Plus 2, still infinity. Which is the same thing we observe by looking at the picture. Is that okay?
Yeah.
And this would be like the level of difficulty that I think would be appropriate for, like, if I asked you on a test or quiz to find the range algebraically, I'd pick something that was all increasing or all decreasing, like this, where it's just fairly straightforward. I wouldn't give you something where there's like, oh, there's like 3 parts to it, and some of it's increasing and some of it's decreasing, and just make it a big, like, gross mess. Would not give that something like that to you. Follow-ups to this one before I go on to somebody else. Okay, Chanel.
Oh yeah, I had a question about this one. So why does it matter if it's like increasing or decreasing? Why does that matter?
Because if this was decreasing, then they get plugged in opposite places. So the upper bound from the domain will give you the lower bound for the range, and vice versa. So that's why it mattered whether it was increasing or decreasing. Yeah. Follow up to this?
Oh, no, it's fine.
Okay. So there are a couple in front of you. Tessa, I think you had your hand up. 10? Yeah, sure. So we're looking at the domain for 10. I notice that I have a denominator. So I know that that can't be 0. And I also have stuff under a square root. So I know that that has to be greater than or equal to 0. You agree with that? If I square both sides, I'd have x is not equal to 0. But if I look at these two together, if I have something that cannot equal 0 and something that has to be greater than or equal to 0, isn't that just the same thing as saying has to just be strictly greater than 0? It is. So that's going to be my domain. Is that cool?
Yep.
You're welcome. Braden.
Can you go over the please?
Yeah, sure. So again, I'm going to do it over here. We have a denominator. So we know that that part cannot equal 0. Now, this is a quadratic equation, right? To solve a quadratic equation, you probably have 3 reasonable methods to solve something like this. You could use the quadratic formula. You could factor this. It's going to be easy to factor. Or you could just use a square root, since there's only a x squared term, there's no bx term. That's what I would do. So I just add 1 to both sides, square root both sides, so I make sure I generate my plus or minus. And so I have everything from negative infinity to negative 1, everything from negative 1 to positive 1, and then everything after positive 1. And that would be my domain. Notice that in doing this, the only values not included are negative 1 and positive 1, which is exactly what it states above.
Yeah, I'm just confused if I have 2 unions.
Yeah, yep. You can absolutely have as many unions as you need. 100 if you wanted. Let's not, though, right? Madison, did I see your hand up at one point?
Yeah, that was fine.
Okay, so you're good.
Yeah.
Good, okay. Any other questions before we dive back in? We're doing okay? Homework's gone all right so far? Not too confusing? Just the right amount of confusing? Okay. That sounds nice. That sounds nice. I think last time we had gone up through section 1.4. Am I correct on that?
Yeah.
Okay. So today we'll be starting with section 1.5, which is all about symmetry. And this is something that's like a little bit of a geometry topic and stuff that you didn't exactly do specifically in Algebra 2. So some of this could feel new to you, and that's okay. It's probably what it should feel like. We're going to talk about 3 types of symmetries. The first is symmetric with respect to, so I'm going to abbreviate that phrase as WRT, with respect to. It's a common math phrase and it comes up several times in this section, so I'm just like saving myself some letters. I'm not being lazy, I'm being efficient. So we have symmetry with respect to the x-axis. So what is that going to look like graphically? So it would look something like this. What should you be noticing? That if I take the stuff above the x-axis and I reflect it across the x-axis, I should get exactly the part of the graph that's below the x-axis. And vice versa, right? That the x-axis acts like a mirror. You guys cool with that? Okay. So if this is the point A comma f of A, this point down here would be A comma negative f of A, right? Everybody agree with that? So what are we really saying here? I'm saying that f of x has to equal negative f of x. So think about it this way. If this was like 2, 3, and this was like 2, negative 3, if I did 3 should equal like negative of negative 3, right? Or negative 3 would equal negative of 3. You guys kind of see what we're doing here? Since they're both y coordinates for the same x. Do you suppose we care a lot about things that are symmetric about the x-axis? Nah. Why not? It's not a function. Yeah, if you're symmetric about the x-axis, you're not a function. Not terribly interesting to us. Most of what we care about are things that are functions. Everybody's cool? Okay. So, what other type of symmetry do you suppose we have? The y-axis. Yeah, symmetric with respect to the y-axis. And again, what is that going to look like? Well, if I take the stuff on the left side of the y-axis and I reflect it across the y-axis, I should get exactly the stuff on the right side of the y-axis. Right? That should make sense. So if this is the point A comma f of A, if that's a point, I should also then have the point negative A comma f of A. Everybody agree with that? Right? So what we're saying then is that f of negative A has to give me f of A. That's our algebraic description. And these type of functions that have this symmetry get a special name. We call these guys even functions. We okie dokie here. No biggie, right? At least not yet. Yeah. So if this is like 2, 3, and this is negative 2, 3, f of negative 2 has to be 3, which is the same thing as f of positive 2, right? So f of negative a equals f of a. Does that feel okay? Cool. So the third one, we have symmetry with respect to x, symmetry with respect to y. The third one should be
Origin.
Yeah, so we call this symmetry with respect, oh, I'm sorry, not that. We call it 180-degree point symmetry with respect to the origin. But that's equivalent to saying symmetry with respect to the line y equals x. Same difference. Good on you guys for remembering that, though. That's pretty sneaky. What does this look like graphically? So if we have something like this, what you should notice is that the stuff to the left of the origin, if I first reflect it across the x-axis, and then I take that and reflect it across the y-axis, it should give you the stuff to the right of the origin exactly. And then, again, the order in which you do those reflections doesn't matter. You could reflect across the y first and then the x. That still give you the same thing. So you had reflections across, or symmetry with the x, symmetry with the y, and then like a double symmetry, right? So algebraically, what is this saying? If we have the point a comma f of a, we should also have negative a, negative f of a, right? Or that negative f of x, I'm sorry, f of negative x equals negative f of x. And these guys get a name too. These are called odd functions. So again, illustrating with numbers, right? This helpful to do the numbers? So if we do f of negative 2, that is negative 3, which is negative of f of 2. I'll pause and take a drink here and let everybody catch up. That looks like they're still writing. Chanel.
May I go to the bathroom?
Certainly. Sure. No problem. You ready to inch forward here? I don't want to leave anybody behind that's still thinking and or writing. But if you are, holler at me and we can pause still a little bit. Now nobody lose their minds here just because we used the P word in math class. The directions on this example say prove if the function is odd, even, or neither. I know. Just relax. It'll be okay. First thing we should do, let's look at the picture so we can figure out which one of these three things I should be proving, right? Because I don't know what it is by looking at it. I mean, I do, but like, you don't know what it is just by looking at it. Maybe you do. I don't know. Probably not. X to the fourth plus 1, graph. Aha! What do we see here? Odd, even, or neither? Even, right? Everybody agree that the left-hand side looks like a reflection of the right-hand side? Okay. So let's prove this. To prove this, what we need to show, or what I want to show, that's what WTS is short for, is want to show. And then I'm just going to take that algebraic definition for even and say I want to show f of negative x is equal to f of x. Once I've done that, that's my algebraic definition of an even function. I'm done. So that's all I need to show. When I'm doing algebraic proof, the standard is typically going to be start with the left-hand side and work until we get the right-hand side of what we want. Everybody's good with that? So I'm just taking this. My goal is to end up with that. Okay. So, f of negative x. What the heck am I supposed to do with that? What if I had f of 2 there? What would that mean? Would mean I just plug in 2, right? For x's. Everybody agree? If I had x of negative 7, what would I do? Plug in negative 7. If I had x of a, or f of a, what would I do? Plug in a. If I have f of negative x, what am I going to do? Plug in negative x. Everybody happy with that? So we're going to have negative x to the fourth plus 1. Everybody's cool? What does negative x to the fourth mean? It means negative x times negative x times negative x times negative x. How many negatives do we multiply? 4. When I multiply 4 negatives, I get positive. And x times x times x times x is x to the fourth. What do I notice here? That is f of x. So I am done. Right? I've just shown that f of negative x is equal to f of x. Booyah! Notice there was no definition stated other than the thing that I wanted to show. There's no theorems used. There's no 2 columns. I'm just stringing together a bunch of equalities. This is an algebraic proof. Different than your 2-column geometric proofs you would have done in your geometry class. Was this a little better? Not so bad, right? Yes, sir. Absolutely. All right. Next up. All right. First up, let's type this bad boy into our calculator and take a look at the picture. Because probably can't tell by looking at the equation what's it gonna be. Looks odd to me, right? Cool. So let's prove that then. To prove something's odd, we want to show f of negative x is equal to negative f of x. And just like before, I guess here, let's call these g's, right? I don't want to get anybody confused here. So g of negative x, what do I do with that? Plug in negative x. Yeah, just plug it in, dude. All right. I will then. If I have negative x to the third and I simplify that, what do I get? Negative x to the third, right? 3 negatives is a negative. So I just end up with negative 2x to the third. 3 times negative x is negative 3x. And I'm looking to get negative g of x. So the next step I'm going to do is factor off a negative. Everybody's good there? And what do we notice about the stuff here? It is exactly g of x. So what can I say? That this is negative g of x. And we're done. Doo-doo! Wow! Is this going okay? Pretty okay? Yeah. I'll take it, right? All right, one more. Your student logic would tell you this one should be neither, right? Because if your teacher says it's going to be one of 3 things and then they give you 3 examples, it'd be some bad teachering not to cover all 3 cases. And you don't know this yet, but I try hard not to do a lot of bad teachering. Maybe you do know this already. I don't know. Occasionally it happens, though. Best laid plans of mice and men, anyways. Well, of mice. All right. So go to the calculator, type in this fella here. Let's hit the graph. Wow. It's not a very good picture, is it? No. To get, where is more of the graph located? Up. So we'll change our window. What part of the window needs to change to go up? The y's or the x's? The y's. And do I want, so right now it's saying the bottom of my graph is at negative 10 and the top of the graph is at positive 10. What should change? The top should get bigger or smaller? Bigger. I don't know, let's guess 30. That seems probably like enough. That's a bit better, right? Okay, odd, even, neither. What do we see? It's not even. Why is it not even? Look at the parabola. There's more of the parabola on the right side than the left side, isn't there? That's why it's not even. This is neither still. Everybody's cool? Okay. I just want to check, guys. You know? Okay. So proof. What do I want to show that it's neither? Well, I got to show that it's not even. And we have to show that it's not odd. Cool with that? Pure stretching? Stretching? Okay. I saw the hand. I couldn't tell behind Holden what the looked like maybe a stretch pose because you put it down right away. Everybody's cool with that plan? All right. Notice what's the nice part here is that they both start with h of negative x, so I can really kind of do this in one line. So again, h of negative x, we're just plugging in negative x's. Cool with that? Let's simplify things down. Is that okay with everybody and how I simplified? Compare that to our h of x. Are they identical? No, what's different? Yeah. So what can I say? Well, that's not h of x, so I know it's not even. Everybody agree with that? All right, let's check the odd. To check if it's odd, I'm going to factor out a negative sign. Is the part inside the parentheses identical to h of x? No, right? So what can I say? It's not odd. If it's not even and it's not odd, it's not gotta be neither. So I'm done. You guys feel okay with what we just did here? Did you do this in your Algebra 2 class? I kind of doubt it, right? Yeah, that's okay. Not terribly complicated thing though, right? Medium complicated maybe. All right. That's it for the symmetry section. Whoop! Here we're going to talk about asymptotes. Okay. Yes. Sure. Do we use that notation here? No. Okay. Morgues. Yeah. Is that cool?
Yeah, it's fine.
Yeah, keep calling it that.
People call me that. Anyways,
You feel like a morgues.
She is a Morgs.
so I'm a little puzzled on like the negative 4x squared,
Okay.
the green stuff. I'm
Yeah.
a little confused what you did there.
Okay. So all I did was I took this and factored out a negative sign. So everything that was positive turned negative and everything that was negative turned positive. And I did that because I wanted to check for negative h of x. So I took that negative sign out, if this, and then checked to see if that stuff was h of x, which it wasn't because the signs were wrong. Does that feel okay? Are you sure? Okay, I'll take it. Tessa, you had a hand.
No, same question.
Okay, you feel okay though?
Yeah.
Okay. Okay. Again, stop me if you can stop me and ask. That's okay. I want you to do that. Chanel.
How come in example B, we didn't like take 2x cubed minus 3x if we did in like that example? Like for this one we just said minus and then put parentheses 2x cubed plus 3x. But then in the example after it was like minus minus. Like,
Well, it's because when I factored out the negative, all the signs change,
oh, okay.
right? So here, this becomes negative, that becomes negative, that became negative,
Okay.
right? So just depended on what the signs were when I factored out my negative. Yeah, no problem. But that was what you needed? That did it?
Yes,
Okay.
thank you.
Yeah, no problem. All right. Asymptotes. What is an asymptote? Yes, sir.
Like a line on the graph where it'll approach it, but it'll never like hit it.
Great. A line that the graph approaches but does not touch. Now, for our purposes, let's say we have something that looks like this. Are we going to count this as a horizontal asymptote? Right now we will. Okay, we're not going to be too picky. Technically, this is not an asymptote. Why? The graph crosses it. What would we call it more generally if it's something like this? It's not quite an asymptote. Do you remember from Algebra 2 what we called those? They're called end behaviors. Because if I look at the end of the graph, it's going to act like an asymptote, even though it might cross somewhere in the middle. But the ends of the graph, we have that same asymptotic behavior, which is a pretty fun sounding smart word if you're able to work it into a sentence. You know? Is everybody okay with this? Okay. So, how can I confirm that something is an asymptote? I can look at a picture and go, okay, visually that looks like it. And if I know a lot about the function, I can remember like my rules from Algebra 2 about like rational functions, and I can use those rules. But what if I'm just like, bless you, you're welcome. But what if, what else could I do? What if I didn't remember any of my rules from Algebra 2? And what if my teacher is asking for justification beyond the graph? Well, if I look at the numerator, I notice that that doesn't factor because there aren't two numbers that multiply to give me -3 and add to give me +3. But the denominator does factor. 3 and negative 1 multiply to give me negative 3 and add to give me positive 2. Everybody okay with that? So I noticed that I should have vertical asymptotes at negative 3 and at positive 1, right? But that's just a rule. I mean, all I really know is that the function is undefined at those values. I'm not really using any kind of evidence. What I could do is I could look at a table of values. I could look at a table of values that were a little bit less than negative 3. And then a table of values that were a little bit bigger than negative 3. And look at what's happening with the y coordinate and see if it's approaching a specific value or if it's like diverging off towards infinity or negative infinity. Everybody's okay with that? Now, this is going to be something pretty annoying to keep typing like negative 3.1 into and replacing that a bunch of times. So what I'm going to do is I'm going to do it the smart way. I'm going to type this function into my calculator. So I'm going to do alpha y equals, and then pick the fraction command. Okay, everybody cool here? I'm just typing this in. Okay, I'm going to exit back out of there. And then what I'm going to do is I'm going to press the vars button. Vars is short for variables. I'm going to move over to the yvars command. So these are the variables that are in the y equals menu. Our calculator for first semester will always be in function mode. So I'm going to pick the function option. I'm going to pick y1. And what this allows me to do is basically just use function notation. So I can do y1 of negative 3.1. So what the calculator did is it just plugged negative 3.1 into this. And then I can try negative 3.01 and negative 3.001. And what do we notice is happening as this is getting closer and closer to negative 3 from the left side? It's getting smaller and smaller, right? What do we say is happening here? The value for y is approaching negative infinity, right? So I might say as x approaches negative 3 from the left, y is approaching negative infinity. You guys agree with that interpretation? Now let's look at what's happening from the right side. So here we got positive 92. Positive 969, positive 9,700. What do we notice is going on? Getting bigger and bigger and bigger, right? So here it looks like as x approaches negative 3 from the right side, we're heading towards positive infinity. So that's what we're noticing here, is that somehow at negative 3 from the left, the graph is going down, and from the right, it's heading up. Maybe I'll do like just that part. Everybody kind of agree with that's the evidence that we're seeing from our table? Everybody's okay that I didn't actually write down the values in the table, that I just looked at them on my calculator? if I asked you for a table of values, you could write those down, but like in the interest of time, I'm just not going to copy them all in there. You're good? Okay. Yes, Chanel.
Didn't you factor the bottom of the fraction at the top of it?
Well, the top didn't factor,
Oh, okay.
right? There's not two numbers that multiply to give us -3 and add to give us 3.
Mhm.
That's fine, because it's just not, it's not factorable over the integers. Yes.
So can you basically just type in the first like information and then just from there do everything?
And look at the picture
Yeah.
and not have to factor it?
Yeah, is that okay?
Yeah, that will work. Oops. So if I just typed in the picture that we had seen here, oh my goodness. Well, I also typed in the wrong numbers apparently. I had a cube there instead of a square, great googly moogly. Those numbers still were fine, it was doing the right things, but should have looked like this. Now, we see a vertical asymptote here at -3, and then another here at +1. We could make the same table at 1, right? By doing a little bit before 1 and a little bit after 1. Do you guys notice there's a horizontal asymptote here also? What does it appear that horizontal asymptote's at? Looks like 1, right? What kind of table would I need to make to confirm that? Well, I'm going to pick some values as x is getting really small, and then pick some values as x is getting real big. And see what the y's are happening. Does that make sense to everybody? And hopefully that's settling down towards the value of 1. Oh, bollocks. All right, all right. So it's giving me a fraction here instead of a decimal, which is fine, but like, I'd rather look at the decimal. So if I do math and then choose the decimal command, it'll take any fractions giving me turn into a decimal. Oops. So now when I recall, I'm just going to have to do second insert, which is fine. So I'm doing this. What are we noticing? We're getting closer and closer to 1. Now we'll just go from the other end. So here I'm going to start with the big one just so I can not have to like add things in also. But we saw as we're getting closer and closer to 1 as we get further and further out, right? You guys see that also? So that would be good evidence for the horizontal asymptote. How do you feel about that? Do you have to do both ends? Yes. Pierce.
I thought that there, like, because there's the middle line that goes through 1, so then, like, how is still horizontal asymptote at 1? It's like the middle line goes through.
We're just going to call those still horizontal asymptotes for now. If you want to be more specific, we call it end behavior. And then we'll be very technical about it, but it's asymptotic either way, right? If you look at the far ends, they're both doing the same thing, whether it's crossed in the middle or not. That's the gist of it. Does this feel okay about how to make a table to confirm something's an asymptote? Okay. That's it for 1.6.
Apple, she's right. She's right.
So let f and g be functions with intersecting domains. Then, for all values of x in their codomain, the following are true. F plus or minus g of x is equal to f of x plus or minus g of x. Notice the plus or minus there is like, if you want to add them, then you add them. If you want to subtract them, you subtract them, right? I'm just combining two formulas into one. F times g of x then is f of x times g of x. And f divided by g of x is equal to f of x divided by g of x, provided g of x is non-zero. What's the weird part of this definition? Why do they have to have intersecting domains? Why is that like the first thing it's stated? Well, let's say the domain for f of x is like, 2 to 10. And the domain for g of x, let's say, is from like -6 to 4. Everybody's okay with that? So if I wanted to do f plus g of -5, I would do f of -5 times g of plus g of -5, but what's the problem? That's undefined, right? Ugh. Notice that the intersection of these two domains is 0 to 2. So if I did the same thing, but I did 0, that would be okay, because I can do f of 0 and I can do g of 0. That's why they need to have intersecting domains, because you need something in their codomain, because if you don't, you're just going to have a bunch of undefined mumbo jumbo, and can't say undefined equals undefined. That's nonsense. Do you guys get what I'm saying? So let's look at an example here where we put this to use. Say f of x equals 2x minus 3. And let's say g of x is equal to square root x plus 2. So let's say I want to do f plus g of x. Well, Mr. Kulik, this is like some easy stuff right here. It's just f of x plus g of x. So I have 2x minus 3 plus x square root of x plus 2. Can I combine any like terms after that? No, man, I'm done. Oh, Mr. Kulik. Well, I didn't say it had to be hard. What if I do g minus f of x? What am I going to get here? Well, g of x minus f of x. So that's going to be this, right? That look good to you guys? I tricked you all. This is wrong. What's the mistake? Got to distribute those implied negatives. Woo-hoo! Ha ha ha! Snookered you all. Who's embarrassed? You can be honest. Be like, I should have caught that. I knew better. Right? Now that you see it, you're like, yup, you got me, Mr. Kulik. Shame on you. No, shame on you, sir. I'm just trying to be funny. No, nothing. You were all joked out at the end of the day, probably. I get it. G times g of x. Well, g of x times g of x. What's the square root of x plus 2 times the square root of x plus 2? Square root of x plus 2 squared, which simplifies down to x plus 2. Is that what you guys want to say? Everybody agrees with this? Shoot. Tricked you guys again. Not plus or minus, but absolute value. Because if x plus 2 was negative, could you have taken the square root of it? No. So it had to be a positive value in order to come out of this thing. Oh, Mr. Kulik, you're so sneaky. I probably wouldn't penalize you if you didn't put the absolute value there, but it should be there. Well, there's a difference between like technically correct and a reasonable expectation, right? I just want to be clear that Mr. Kulik is like a reasonable and understanding person, but he wants to make sure that you know when he's giving you a break versus what's right. You know what I mean? And I don't mind giving breaks on stuff where it's like, oh, that's not technically correct, but like, let's just not be that anal right now. You know? Anyways. So that's that. So there we go there. What do you think? That correct? Now you're all second guessing yourselves, right? I've destroyed all your confidence by throwing out the trickies or the technicals. Okay, so is it incorrect to have the square root in the denominator? The answer is no, it just might not be following directions, right? Like 1 over the square root of 2 is still equal to square root 2 over 2. Those are still the same number. It's a question of like preference. So let's establish what the preference is for this course right now. Deal? Okay. If there's a variable under your radical, I don't need you to rationalize. If it's just numbers in your radicals, I expect you to rationalize. Deal? Okay. So I think this is fine the way it is. You want to hear something else about this rule about no square roots in the denominator? Eventually you get to a point in mathematics where your teacher's going to be like, stop doing that. Stop. Just stop. It makes it worse. Now it doesn't make it so worse right now, but just to let you know, that's merely a convention that eventually is going to go away. Where it's going to be like, yeah, that's you're making life way harder than it should be right now. Be like, oh, okay then, I'll just stop. Deal. You get to like Calc 3 and your professor's going to be like, oh, please stop. Please stop. Anyways, so there's a fifth operation, basic operation between functions, aside from addition, subtraction, multiplication, division. Does anybody remember what it is? You would have done it in Algebra 2 last year. Starts with a C. Composition. No? Does that ring any bells? So if we let f and g be functions such that the domain of f intersects the range of g, then the composition f of g, which we denote with the little open circle, or we can just write it as like a function notation. Okay. Pet peeve for Mr. Kulik time. How do you read this? F of g. It is not fog. I don't want to hear anybody saying fog of x. All right? I know it's tempting. There's no fog in this class. Everybody's good? It's just my pet peeve. It's not wrong. Well, I mean, it is wrong, but it's like, it just drives Mr. Kulik up the wall. And like, I'm happy on the ground, you know? Let's not go up the wall. You guys remember composition now that we put the notation in here? Oh boy. Okay. So let's look at an example. So let's say we have our f of x. And let's say we have some g of x. And let's say we want to do f compose g of x. So what are we doing? We're doing f of g of x. So that's f of negative 3x plus 4. So what do I do when I do f of something? Plug that something in for x. So when I look at f of x, that's 2 times something squared minus 3 times something. What is that something? Negative 3x plus 4. So we got to go ahead and multiply that out. When I do negative 3x plus 4 squared, that's what? That's 9x plus 16, right? Or 9x squared plus 16, right? Everybody agree with that? No! I fooled you again. What do you have to do there? Do exponents distribute? No. What should you do here? You FOIL. Yeah, this is really a FOIL, right? Negative 3x plus 4 times negative 3x plus 4. I know, guys, I know. You're like, Mr. Kulik, I feel so bad about myself right now. I've gotten tricked every single time. It's okay, guys. It's better to get tricked now than like when it counts. Are you impressed that Mr. Kulik can do those in his head?
Yeah.
You shouldn't be. It's not that hard. It's ax squared plus 2bx plus b squared. Or actually, I don't even need the x's in there. This is that's the factoring pattern for a sum of, for a perfect square factoring. So that's all I'm doing in my head. You know what I mean? And then we distribute the 2 through and combine some like terms, right? So that's going to be negative 48 plus 9, so that's going to be negative 39x. And then I have 32 minus 12, so that's plus 20. Well, that was a pain in the tuchus. What if we do g of f of x? Oh, Mr. Kulik, I know what this is going to be. Right? Just got to be the same thing, right? The other thing was f compose g, so this just must be g compose f. G compose f must be the same thing. Everybody agree with that? No! Composition is not commutative. What does that mean? That f compose g is not necessarily going to be g compose f. Ugh! Again, I got snookered by Mr. Kulik. Well, guys, it's okay. It is okay. So if I look at g says I do negative 3 times something plus 4. What's that something going to be? F of x. Is there a bird in the classroom? And here we can see definitely not the same, right? Oh no! Important piece to realize. Do you guys feel okay with doing these compositions? We're just plugging one into the other and doing some simplifying. It's okay? You do some more practice, they'll come back pretty quick. It's just grinding through some algebra. All right. Yep. Definition. Let f and g be functions.
Wait, is there like a word for this?
Mm-hmm. We say that g is the inverse function of f, provided that the following holds. F of g of x is equal to g of f of x, which all equals x. So in this case, we would call this g of x. We would name this guy f inverse of x, and we'd write that f inverse as a -1 exponent attached to the function. Does this look familiar? Okay. So what is really happening here? So if I do f compose f inverse of 6, what should come back out? 6, right? It's the equivalent of doing nothing. So that f undoes whatever F inverse is doing, right? So if I have some mapping diagram, and say this is my F, so that's my domain and my range. If I wanted to draw the mapping diagram for F inverse, the range for F inverse should be, or the domain for F inverse should be the range from F, and then they're just going back from whence they came. So F sends 1 to 4, F inverse sends 4 back to 1. F sends 2 to 6, F inverse sends 6 back to 2. F sends 3 to 5, F inverse sends 5 back to 3. Everybody's okay with that notion? What if we have our function defined as a set of ordered pairs? What's F inverse going to be then? Okay, 8, 5. What else? 8, 3. Yep. 6, negative 1. And then 4, negative 2. Uh-oh, what do you notice here? Yeah. Nice work. So we should notice that F inverse here failed to be a function. Oh no! Okay. Oh boy. Let's stop at this point. This feels like a good stopping point. Let me put a note in my paper. Just FYI, you guys could now do up through
5 to 18. I did there, but I don't know. Stuff like
30. Up to 30, yeah.
What, 5 to 30 for this?
Right. So I think we stopped, where did we stop at? 18?
Yeah.
So 19 to 30 now?